Hello, good afternoon, everyone, and thank you for very much for joining this webinar today on application of line differential protection in medium voltage distribution lines. My name is Oscar Pereira, and I work in the commercial department at ZIB. Today's event is part of ZIB's 2025 training plan that includes free online sessions like this one, as well as paid in-person training sessions that we organize in Bilbao and Barcelona. So, well, in any case, the details about our training offerings are all available on our website, zibautomation.com. Today's session will last a total of 30 minutes, and with 20 of those dedicated to the topic presentation itself. And then the remaining 10 minutes will be dedicated to attend your questions and to clarify any points or whatever, okay? So before we start, I encourage you to click on the display button that you will find on your screen, on the lower side of your screen, and please select the full screen option. This way, you will definitely have a better viewing experience. And also, at the same time, please, any question that you may have, just drop a message using the chat feature that you will find as well in your screen, okay? At the end of the presentation, after the last the 20 minutes, I will share with all of you the questions that we receive. So at this point, I am pleased to introduce you our colleague Roberto Cimadevilla, that he is our application manager. So, hi, Roberto, are you there?
Yes. Okay.
Hello, please.
Okay, I will share my screen. I don't know if you, Oscar, can you see my screen right now?
No yet. Okay, here it is. Here we are, yeah.
Okay. Okay. I'm gonna share. Okay, so, well, as Oscar said, I'm going to talk about the application of line differential protection in medium voltage distribution lines. We presented a similar webinar about protection in medium voltage distribution lines, but instead of talking about line differential, we talk about distance protection. So I will focus on line differential. So I will start first of all about talking about the problems of overcurrent protection in medium voltage distribution lines. That is the main protection function that is used in this type of lines. Then I will propose using line differential protection, which is more selectable than overcurrent protection, but we will see the cases that make the application of line differential protection difficult. We will see the RTDS model, simulated cases, and I will end up with some conclusions. So the medium voltage distribution networks that are exploited in a meshed way are increasing right now to improve power quality and availability of the networks. And this creates problems for overcurrent protection. First of all, because we have topology changes. The remote breaker of these lines can be open or closed, and this changes the fault current, which affects very much the overcurrent protection. There are bidirectional power flows that also affects overcurrent. And we have in-feed or blinding due to distributed generation or remote in-feed. So here we can see in-feed from a distributed generation and in-feed from a remote end. So in both cases, current B is higher than current A, and this creates selectivity problems or coordination problems between relay A and relay B. Also, we could have renewable energy sources generation in source E1, and this will create a low fault current, which also creates problems for overcurrent protection. So instead of using overcurrent protection for these mesh distribution networks, we could use line differential. This is the model that we will use for studying the application of line differential protection. So here we have 2 tap loads and 1 tap generator. And even though line differential protection is much more selectable than overcurrent, it can also have problems when applying to this type of medium voltage lines. First of all, because the line differential will just measure the currents at both ends of the line and will not measure the current in the loads or in the generators. So this creates a false differential current. And the main cases that makes line differential protection application difficult are the following. First is a fault at the low voltage side of the MV-LV transformers, which will be fault F1. Then inrush currents of the MV-LV transformers when we close circuit breaker 1. Then external faults, which will be F2, and internal faults, which will be F3. So we will analyze each of the cases to see the behavior of line differential protection. So starting with the first case, which is a fault at the low voltage side, we need to set the pickup value of the line differential above the maximum fault current. And to calculate this maximum fault current, we will consider the minimum transformer impedance. So we will use this formula to calculate the fault current. This normally gives a high pickup value, so it loses sensitivity for the line differential. So we could use distance supervision. We could use zone 2, for example, set to 120% of the line, so that we could reduce the pickup value, making the line differential operate only if the zone 2 activates. And this could increase the sensibility of the line differential protection. Normally, the transformer impedance is much larger than the line impedance due to its low power. So normally, faults at the low voltage side are much far away from zone 2. We will see later in the simulated cases. On the other hand, MV-LV transformers are normally delta Y. So when there are faults on the low voltage side, there is no neutral current. So we could use a neutral line differential protection to increase the sensibility in medium voltage faults with high fault resistance. This is quite selectable differential unit, as it will not operate for faults at the low voltage side. The other case is inrush of the MV-LV transformers. When we close this CB1, this circuit breaker, we will generate an inrush of the line of the transformers and also of the loads at the same time. So distance supervision will normally not activate during the inrush. We will see in the simulated cases that the impedance is far away from zone 2. So if distance does not operate, line differential will not operate either. Anyway, we have to use harmonic blocking for the line differential protection. And even though delta Y transformers do not generate a neutral current during inrush conditions, if there's any CT saturation, a false neutral current can be generated. So harmonic blocking must be used not only for phase differential, but also for a neutral differential. It is important to analyze the second harmonic content because this is not a typical inrush current, but a load current is added. So this decreases the second harmonic content. So this is the waveform that we normally get. And we can see this is not the typical waveform of an inrush condition, but we will check later in the simulations that the harmonic content is above the typical threshold of 20%. Regarding external internal faults, F3 and F2, the currents that flows to the tap loads is normally quite low. So the line differential unit is not very affected by the tap loads. But the current that flows from tap generators should be considered, and it affects the line differential function. If we have renewable energy sources as tap generators, the current that injects these sources is quite low, around 1 per unit. But if we have conventional generation, it can inject considerable current. So in order to operate correctly or avoid erroneous operation of line differential, we can use a positive sequence pure directional unit to distinguish between internal and external faults. We will see now that this unit is quite selectable. Harmonic blocking can operate during internal faults with CT saturation, so it is important to use an unrestrained differential unit to treat during internal faults. So regarding the directional comparison, this unit just compares the angle between the currents at both ends of the line. If these currents are in phase or the directional comparison will detect an internal fault. And if the currents tend to be out of phase, it will detect an external fault. So just focusing on the positive sequence directional comparison unit, this is the positive sequence pure network that we have for an internal fault at this point. This represents the positive sequence impedance of the distributed generator, and we can obtain the angle between the ratio between the two currents that follows this formula, with zeta bar is following this formula. So if we have synchronous generation, this angle will tend to be around 90 degrees. So the angle between both currents at both ends of the line will tend to be around 0 degrees. And if we have rest generation, renewable energy sources, the angle could be much higher than 90 degrees, but the module will be very high because these sources are weak sources. So the angle will tend again to be around 0 degrees. So if we have 0 degrees, the unit will detect an internal fault. For external faults, we can conclude the same as for internal fault, but the current at the N2 will be 180 degrees phase shifted. So the angle will tend to be 180 degrees. So the currents will be out of phase. So it will detect an external fault. Okay, this is the RTDS model that we have used. We have two underground sections and one overhead section. And we have 3 tap transformers with 6, 2.8, and 4.2 MVAs. So we will see all the cases we have seen before in the simulation. These are the relay settings. We could set line differential according the maximum external fault current, and this will be calculated with this formula, considering the minimum transformer impedance that will be 2000 amps, which is 1.66 per unit. If we use distance supervision, we can increase the sensibility, we can decrease this setting, and we can use the maximum load instead of the maximum fault current to set this pickup value. And we could use a 0.5 per unit to increase the sensibility. Distance supervision, we use a zone 2 set to 120% of the line impedance, which will be 2.25 against the minimum impedance of the tap transformers, which is 15 ohms. So we will see each of the cases now. So for faults at the low voltage side, for a three-phase fault, we can see that the phase differential current is 0.6 per unit, so it is above the pickup value selected. But if we use distance supervision, we can check that the impedance is far away from zone 2. So distance supervision will avoid the operation of phase differential unit. For AG faults at the low voltage side, we can see that these are the differential currents. The neutral differential current is almost 0. So we can see that the neutral differential unit will not operate for this fault. And for the phase differential units, we can see that the current could be above the pickup value. But if we use distance supervision, we can see that this impedance is far away from zone 2. So it will not make differential unit operate. Regarding faults inside the protected line, this is a three-phase fault at 100% of the line. We can see that there's CT saturation at the remote end. Regarding distance supervision, which we can check that the distance unit zone 2 will operate for this fault, so allowing the trip of the differential unit. But because of CT saturation at the remote end, as we will see before, harmonic blocking will activate. So we need to enable an unrestrained differential unit to trip this fault. This is an AG fault at 100% of the line. Also, CT saturation occurs at the remote end. We can see that the distance unit operates correctly, allowing the differential trip. But due to this CT saturation, we should use also an unrestrained unit. And regarding external faults, this is an AG fault at 0%, external fault at the local bus bar. So here, these are the differential units. We can check that for the differential unit in the faulted phase decreases. So this fault is detected by our external fault detector that uses 3 units. The first one uses the ratio between differential and restrained current based on samples, that is these units. And the second ones use phase and positive sequence directional comparison, that is signals 2 and 3. So we detect the external fault and we can block the differential unit in phase A and the neutral differential units with this external fault detector. So we don't see any problem with no distributed generation. In RAS without fault, we can check, this is the inrush currents, and we can check the harmonic content of these currents. The pink line is 20%, so this harmonic content is above the 20%. And also no distance supervision is activated because this is the impedance, which is far away from zone 2. So it will block correctly the differential unit. Close on to fault at 0% of the line, we can see that the harmonic content of the faulted phase and of the neutral is very low, so it can make the differential unit trip, and there's distance supervision activation. And finally, a case with distributed generation, we have generated that fault at an internal fault at 50% of the overhead lines with the distributed generation connected to the third power transformer. We are getting these values for the impedances at both ends of the fault. And if we consider a synchronous distributed generation, which a positive sequence impedance angle is close to 90 degrees, the angle between the currents will be around 0 degrees. And if we consider an inverter-based generation with an angle around 150 degrees, we can get an angle between the faulted currents of around 6 degrees, which indicates internal fault. And for the external faults, the angle between the currents obtained was close to 180 degrees, so allowing the detection of an external fault. So to conclude, tap loss generation creates a false differential current during load, fault at the low voltage, and transformers inrush. Distance supervision allows better sensibility of the phase differential unit. External internal faults are not very affected by tap loss, but may be affected by tap generation, especially conventional generation. Pure fault directional comparison unit correctly distinguishes internal and external faults with tap generation. And a neutral differential unit should be enabled as it does not operate for low voltage faults due to the transformer connection group, delta Y. Harmonic blocking should be applied not only to the phase differential unit, but also to the neutral differential unit. And unrestrained phase differential unit should be used to detect internal faults with CT saturation. And this is everything. So I wait for the questions.
Thank you, Roberto. Thank you so much. Yes, the channel is open, so I encourage the people attending the seminar, any question, clarification, or even experience that you may have, please share with the audience, and we will be happy to discuss this with Roberto. For the time being, there's no questions, Roberto, but I take this opportunity first to inform some of the people connected that I realize that some of them are following us from Spain or Portugal, that we will be repeating this same webinar today at 3 p.m. in Spanish. So in case you want to follow this in Spanish, or to reinforce all the topics, well, today at 3 p.m. we will be here again in Spanish. So again, in the meantime, please, any questions, put in the chat. In any case, also I will share with you a link so that you can download this presentation in PDF that Roberto prepared. So for future, for future information or whatever, you can have the PDF with you with all the comments. Okay, here it is. The link is there in the chat, so you can copy the same and download the presentation at your convenience. So, well, as there is no questions for the time being, still we have 5 minutes to go. So, Roberto, just one question, as you are in close contact with customers. I think that imagine for a customer that is just a pure distribution company, not a transmission, but a distribution company, I guess that in some cases for them, the use of a line differential could be a challenge, because probably they are not used to operate or to prepare settings for a line differential relay, but just for overcurrent, transformer diff, etc. So do you have any experience on how other distribution companies approach this issue, or I don't know, any real situation that you have been involved?
Well, this RTDS model that we have used comes from a real line belonging to Iberdrola that is applying line differential protection on the 33 kV lines because it is a meshed distribution network. So it is very, very difficult to protect these lines with overcurrent. Anyway, this is a special application because this is not the same as protecting a transmission line where you don't have taps. So that's why they have to study this application to see which units they should enable. And it is, you have to have this harmonic blocking, like if you were protecting transformers inside the line differential to do this application. So I think this presentation can be a base for other distribution companies that find this problem of protecting this kind of lines with overcurrent and to change to a line differential. We have also presented the option of protecting it with distance. So I think this should be considered for calculating settings and deciding which units should be used.
Yeah. Okay, I see. Okay. So yeah, Eloy, Rufato, thanks for the presentation. Okay, muito obrigado, José. No, there's no more questions, Roberto. So probably I guess that the audience needs maybe to study carefully your presentation, the PDF. So of course, for everybody today, feel free to contact myself or any of the people in ZIB for any questions that you may have after this presentation. So I think we can conclude this session today. So thank you, all of you, for your participation, for your presence. By the way, just the last link that I will share with you, this one. Here in this link, you can check the different webinars that we will be offering in the future, okay? So it's a good opportunity to stay tuned with us and join any future webinar that you find useful. So once again, thank you very much to all of you, and we look forward to seeing you next time. Thank you.
Bye-bye.